Nice. All right, so you guys have talked about extrema before, like local extrema, relative extrema, which are the same thing, like local max, local mins, right? And you guys have talked about absolute max and absolute mins, like especially in pre-calc, you guys have talked about that. Well, we're going to be talking about that here today, but we're using calculus. Be careful with just copying this stuff word for word. Probably read it a little bit and let's just annotate it. Maybe take the keywords I say, or if I repeat something a whole bunch, write that down. So we got relative extrema, which would be local max or mins, right? So if there's an open interval containing C, open interval means we're not including the endpoints, right? On which f of C is a maximum, then f of C is called a relative maximum. So that means that relative maximums or local maximums have to occur on an open interval, right? So if we have some open interval and we have a local max or min, how would that look? Like when you guys talked about this stuff last year, what do you guys know about local maxes or local mins? How would it look? So you said like a U, if you have a U, it's the very top, like that. Okay. So a frown and a smile. Okay. What about this? Would that be a local max or min?
Yes.
How about this one? So for relative extrema or local extrema, we can say they're the hills or valleys. Local and relative mean the same thing. Okay, local max, local extrema, relative max, relative min, relative extrema mean the same thing. Okay. They're just the hills or valleys, guys, and they're on the open interval, so we don't worry about the endpoints. Okay, on some interval, open interval, not including the endpoints, a local max is the highest point. Local min's lowest point. Okay, what interval? Well, they got to give it to us. Okay. Okay, local, relative, same thing. All right, so here are a couple graphs. Relative extrema, we got a cubic function. You can clearly see a hill right here. We can say that is a local max of 0, which means the height, at x equals 0. Okay. There's a valley here, or maybe like a dip in the, people call it different things. I say hills and valleys all the time. You can say local minimum of -4 at x equals 2. Okay. What do you guys notice about these hills and valleys in context of calculus? The tangent 0? What do you mean the tangent is 0? So the tangent line is 0? Okay. What else does that mean? Okay. Same thing, but like, what else does that mean? Yeah, derivative is 0. So f prime of x equals 0 at these local max or mins, right? Why? Because you have to have a horizontal tangent line, which create that hill or that valley. Okay. Is that true over on this picture? We have some rational function. Those are fun. Why? Because, derivative is probably creating another rational function, which means you can set the top equals 0. Okay. Looks like the slope of the tangent line will be 0. We have this horizontal tangent line here at x equals 3. What about the v, though, the absolute value? What doesn't exist? The derivative does not exist. Or we can say the derivative is undefined, right? Okay. So where do relative extrema occur? Where f prime of x equals 0, or when f prime of x is undefined. What about a horizontal line? None? Okay. All right, so relative extrema or local extrema occur when the derivative equals 0 or the derivative is undefined. All right, at those relative extrema, the derivative was either 0 or it did not exist, right? Okay. The x values of those special points are called critical numbers. So critical numbers are where the derivative equals 0 or the derivative does not exist. So we might just tell you, find the critical numbers. You have to know what that means. Like that drives you to do something, okay? So if some function is not differentiable at a value c, or if the derivative at c equals 0, then that c value is a critical number. All right. If we have a local extrema, then that x value, which that local extrema occurs, is a critical number. Okay. They might say there's a local max at x equals 4. What can you tell me? Well, maybe the derivative equals 0 at x equals 4, or the derivative is undefined at x equals 4. Okay. So if we already know that extrema occurs, then we can go backwards and say the derivative either equals 0 or it does not exist. Definition of extrema now, which means absolute extrema. Absolute max or mins. If we just say extrema, we mean absolute. Let f be defined on an interval I containing c. We're going to say closed interval. If f of c is the minimum of f on I, which means it is the smallest height for the function on some interval I, then we have a minimum. Conversely, if f of c is the maximum, then we have a maximum on the interval. All right. The extreme value theorem is applying this idea of extrema. Okay, EVT for short, EVT. If f is continuous on the closed interval, then f has both a minimum and a maximum on that interval. If you have a line that has endpoints, there's got to be a highest point and a lowest point. Okay, this sounds really familiar. If f is continuous on a closed interval, well, remember chapter 1, IVT, intermediate value theorem? If f is continuous on a closed interval, the endpoint heights are not the same. Then we get every height in between those two heights, right? Remember that? Could there be more? Yes, but we only guarantee the two. Between the two, I should say. So extreme value theorem states that if we have a continuous function on some closed interval, that means EVT theorem applies. EVT applies. That function has a minimum and a maximum. Our job is to find those values. They ask a lot of questions about this stuff on the AP test. What happens if they ask us to find the maximum value of a function over some closed interval, but that function is not continuous? Then you say, good luck. Can't do it. Right? EVT does not apply. I cannot guarantee a maximum value nor a minimum value on that closed interval because it's not continuous, right? What about this? There's my function f. Is there a maximum? Is there a minimum? They're the same, right? There's a maximum height and a minimum height. They're the same. It's boring. They're probably not going to ask any questions like this. It's going to be more interesting. Okay. All right. Well, guidelines for finding extrema, guys. Here we go. What they say in Mandalorian again? Here we go. This is the way. I'm glad I can find a way to tie that in here. That's nice. Guidelines for finding extrema on a closed interval. Okay. Number 1, find the critical numbers. What does that mean? Set the derivative equal to 0 or find out when the derivative does not exist. Okay. Evaluate f at each critical number. Evaluate f at each endpoint. And why are we testing critical numbers? Those are possibilities that we have a local extrema. Could that local extrema be an absolute extrema? You bet. The smallest value that you calculate is the minimum, the largest value is the maximum. That's simple, guys. In this process of evaluating those x values in the function, we call that the candidates test. So anytime they ask us finding extrema, I'm going to ask you guys, what do we do? You should say, use a candidates test. That should drive what we do. All right. Well, let's first off start by finding the critical numbers. What does that mean to find critical numbers? What's the process? Or find out when the derivative does not exist. Yeah. Okay, so critical numbers when the derivative equals 0 or when the derivative does not exist. Okay, well, this is a polynomial friendly function, so the derivative is going to exist everywhere, right? All right, well, let's find the derivative. F prime x equals, what is that, negative squared. Okay, well, this exists everywhere, so we only have to find out when this equals 0. 0 equals negative 6x squared plus 6x. Notice I didn't say d dx of both sides, did I? We're just finding the derivatives. I'm hoping we know how to find derivatives now, right? We're just going to start applying this knowledge. You do have to write this out. You do have to write this out. If you do not say the derivative equals 0 or set the derivative equal to 0, I have no idea what you're doing. Nobody else will. Okay. Okay, let's solve. Try and do all these problems without a calculator if you can. And then if they don't factor or they're a difficult trig one, easy trig ones won't use a calculator. But try and just factor these. A lot of them will be quadratics or polynomials anyways. All right, I'm going to factor out negative 6x. And then what do we get left? X. And then minus 1. Using a zero product property, set each one of these factors equal to 0, right? You guys did that. Algebra 1, Algebra 2, whatever. Okay, we get x equals 0 from this factor, right? And then we get x equals 1, positive 1, from this factor. Yeah. So how many critical numbers do we have? 2. Okay. Does that make sense? Should we have 2 critical numbers? Why? What's the highest power? What do you mean the highest power? Okay, what's up? How do you know there's 2 turns? Yeah, it's a cubic function, so it's got to turn twice, right? So to be turning twice, you have to have a max of 2 critical numbers, right? That should make sense too, because your derivative is 1 power less. That means you'll have, like what you're saying now, you have 2 zeros. Right? Okay. All right. So we just say the critical numbers are x equals 0 and x equals 1. That's it. That's all you got to do. But now, let's find the extrema. Find the extrema. What does that mean? Candidates test. Evaluate f at the critical numbers and the endpoints. Okay, let's find the critical numbers. So let's set the derivative equal to 0. Well, let's first find the derivative. 12x cubed minus 12x squared Set this equal to 0 and factor at the same time. There'll be x minus 1 again. Oh, this is too easy. X equals 0, x equals 1. So we have two critical numbers, right? Are these two critical numbers on the closed interval that they gave us? Yeah. So we include both. What happens if one of the critical numbers was not on the closed interval? We just exclude it from our candidates test. Okay. Is this derivative ever undefined? No. It's a polynomial. We're good. Okay. All right. Now let's set up our candidates test, which is a T-chart, guys. X, f of x. In this T-chart, I put my endpoints and I put my critical numbers. I like to put them in order also. -1, 0, 1, 2. Okay. So we're already at step 4 now, isn't it? No, we're at step 3. We're evaluating, right? Step 2 and 3 combined, I guess. Evaluating. So we evaluate this x value in the original function to get the actual height of the function. Okay, so 3 times -1 to the 4th minus 4 times -1 cubed. What we got in that? Well, that's 1 times 3, -1 times -4. That's 7 then? Evaluate the function at 0. That one's easy. Evaluate the function at 1. 3 times 1 to the 4th. 4 times 1 cubed. That'd be 3 minus 4, -1. Then evaluate at 2. Well, if I factor out 2 cubed, that's factoring out an 8. So then I have 6 minus 4, which is 2 times 8, 16. What's the smallest number? -1. So we have a minimum of -1. What's the maximum? What's the biggest number? 16. So we have a minimum of -1 and a maximum of 16. These are not x values. These are f of x values. It means there's a heights, right? Well, do we want to know the x values? They might ask us. They might ask us for the actual points. Just use your context clues from the stem. All right, find the absolute extrema. Worded just a little bit different, but the word extrema appeared. Absolute extrema. We know this is candidates test. We have a closed interval, and we have a function. Okay. Find our critical numbers, test our critical numbers and our endpoint in a table. Smallest number is the minimum, biggest number is the maximum. All right. Use all the skills we've learned to find your derivative, whether it's a rewriting skill or any other procedures. You're going to have to use those. All right, I'm going to rewrite this though. The numerator is a 1, so I'm just going to write it as 1 plus x squared to the -1 power. I think that's going to be easiest. Okay? You can use the quotient rule if you want. That's fine. Well, then f prime then is -1 of the stuff to the -2 power times the derivative of the stuff, which would be, what, 2x? Okay, and then I'm going to rewrite this derivative for convenience sake. -2x over 1 plus x squared squared. All right, there's our derivative. Well, when does f prime of x equal 0? Let's figure it out. Well, that would be 0 equals -2x. And then what, x equals 0? We're doing this because we have a fraction. This fraction is equal to 0 when the numerator is equal to 0. All right, when is f prime undefined? Well, it's when the denominator equals 0. Well, in any event, when this inside part is equal to 0, 0 squared, 0, right? Or if you just write it down like this, take the square root of both sides, or square root of 0, 0. So 1 plus x squared equals 0. Subtract 1, x squared equals negative 1. And do we have a problem, Houston? So is there a time at which this derivative is undefined? No. So got nothing here. Right? And we could use our critical thinking skills. We're squaring a value and adding it to 1. That's always going to be positive, right? It's never going to be 0. Okay? Does x equals 0 satisfy the original equation? Is it in the domain? Yep, that's fine. Is it on the interval they gave us? Yep. So there we go. We have one critical number. We have 2 endpoints. Let's make our candidates t-chart. Okay, I got -3, 0, and 1. Plug these values in. Okay, -3 squared is what, 9? Plus 1 is 10, so 1/10. Plug in 0. 1 over 1 is 1. Plug in 1. Get 1/2, I believe. All right, what's the minimum? 1/10. Maximum of 1. There we go. That's it. You have 1/10 of a banana at time t equal -3. Yeah. What do you mean -2 and -1? Because a max or min will only occur at a critical number. And that's it. So we only need to worry about the critical numbers. And then an absolute max could occur at critical numbers or endpoints. So we use critical numbers and endpoints. Those are the only values we need to worry about. In between -3 and 0, it's either climbing or it's falling. Okay, does that make sense? Find the extrema of f of x when f of x equals what? 2 sine of x minus cosine of 2x on the interval 0 to pi. This is how we amp it up a little bit. You start becoming emotional about the problem because there's trig in it. You're like, oh, I don't like trig. Well, nobody cares what you like or do not like. This is not a dating profile. We don't care. Just do the calculus. All right. Well, we find the critical numbers, right? So we find the derivative. F prime x equals, what do we got? Okay, 2 cosine x, then what? Plus 2 sine x? Like that? Look at you guys using a chain rule to bring that constant up in front right away. Make me proud some days. Is this ever undefined? Well, cosine's always defined, right? Sine's always defined. You take 2 numbers, add them together, it's going to be a smooth curve still, right? So it's always going to be defined. So we just need to worry about when the derivative equals 0. Now this would probably be a calculator problem, a calculator active problem. So let's use our calculators and let's find those zeros. What are we looking for when the function equals 0, when the derivative equals 0? Derivative equals 0? Okay, so 2 cosine, and what mode should I be in? Radian. Sine 2x. Enter. Do I need to see the whole graph from -10 to +10? No, I know this, so I'm going to change my windows right away. I'm going to go from 0 to pi. So I only need to see that graph from 0 to 2 pi. I'm looking at the derivative graph. I'm looking at where does that graph equal 0. It means where does it cross the x-axis. Let's find out. There's 1. There's 2. There's 3. And there's 4. So we got to use our find the 0 function or calculate the 0 function. Go find those zeros. So second, calculate, and let's go with 0. Set up your, let's see, does the back arrow work? Yeah, it does. There we go. There's my left bound. Hit enter. Let's go right bound. Hit enter. Hit enter again for guess. There we go. 1.570 if you're truncating. Now we could store that value as A, right, on our calculator if we needed to. All right. Go find the next one. And we get 3.665. All right, go find the next one. Should all be fluent in calculator. 4.712. And then finally, looks like I get 5.759. All right, let's see if I can write in this now. So we get x, sweet. We get f of x. I got 0. The first one was what? 1.571. Second one is 3.665. And again, we can store these values in our calculator, right? 4.712, 5.7, was it 59? And then 2 pi. Now, where do we plug these values in? In what? Okay, the original. So do we have to change anything? We can just go in here and go to table right now. Oh, we gotta change it because this is the derivative, right? All right. Go in here, type something new in. 2 sine of x, right? Was it minus cosine 2x then? All right, go to my table. I'm like, oh crap, I want to be able to plug in my own values. Remember, go to table set, change that to ask. Go back to your table, plug in your values. 0. If you save that first one as A, then just go to alpha A and hit enter, and it'll plug in that value for you. And some change. And some change. Wait, what, 759? And then 2 pi. Ooh, not 2e. All right, what's the minimum? Negative 1.5 looks like, right? Who cares if it happens twice? That's just the minimum height we get to for this function on that interval 0, 2 pi. What's the maximum? 3. There we go. That's all we had to do. Okay, let's see if I can write that. Min of negative 1.5, right? Max of 3. And we could state the x values at which those occur. They didn't ask us to, so we're not going to right now. Questions on that? What's one thing I did not check for at the very beginning of the problem? Like, I might have thought it internally, but I did not outright say it out loud. What's continuous? Yeah, I didn't specifically check to see if this function is continuous on this closed interval, right? But we've worked with polynomials for 2 of them. This one, we stated that it was continuous, right? So I didn't do it at the very beginning. And then this one, we should just check. I forgot to say that earlier. Let's check, make sure these functions are continuous, because if they're not continuous on this closed interval, this extreme value theorem does not even apply. It means we can't find those maximum heights, okay? Any questions on this so far? Seems a lot easier than stuff we've done before.